You might not realize it, but right now, as you're watching this video, you are being absolutely bombarded by waves of energy. These waves are zipping through your body, bouncing off the walls, and streaming down from space. We call this the electromagnetic spectrum, which is a massive range of energy, from radio waves as long as a football field to gamma rays smaller than the nucleus of an atom. I'm Mike with List 25, and these are 25 interesting facts about the electromagnetic spectrum. 25. It's all the same stuff. The most mind-blowing thing about the electromagnetic spectrum is that, at its core, everything on it is made of the exact same thing: photons. Whether it's the radio waves carrying your favorite station, the microwaves heating up your leftovers, or the X-rays a doctor uses to see your bones, it's all just EM radiation. The only difference between a dangerous gamma ray and a harmless light wave is how fast the energy is vibrating, or its frequency. Think of it like a piano. The low notes and the high notes are both just sounds produced by vibrating strings, but the pitch, or frequency, changes how we experience them. In the EM spectrum, that pitch determines whether the energy passes through you, bounces off you, or helps you see the world. 24. Visible light is a tiny minority. We tend to think of light as the main event, but in reality, the light we can actually see, the rainbow from red to violet, makes up less than 1/10 of 1% of the entire spectrum. If the whole EM spectrum were a long road stretching from New York to LA, the portion we call visible light would be about the length of a single deck of cards. We're essentially living in a world of invisible energy. Animals like bees can see into the ultraviolet, and snakes can see the infrared heat of their prey, meaning their version of reality looks completely different from ours. We've had to build complex machines just to translate the rest of the spectrum so we can understand what's happening in the dark. 23. The speed of light is a universal speed limit. Every single wave on the EM spectrum travels at exactly the same speed in a vacuum, approximately 299,792 kilometers per second. This is the famous c in Einstein's E equals mc squared. It doesn't matter if it's a low-energy radio wave or a high-energy X-ray. They are all racing through space at the same ultimate speed. This is actually how we define the meter in the modern world. It's the distance light travels in a tiny fraction of a second. The reason this is so vital is that it means information has a lag time. When you see light from the sun, you're seeing it as it was 8 minutes ago. When we pick up radio signals from the edges of the galaxy, we're essentially listening to a broadcast from the ancient past. 22. Light is both a wave and a particle. One of the weirdest facts about the EM spectrum is that it has a bit of an identity crisis. Under certain conditions, light behaves like a wave, rippling through space like a wave in the ocean. But in other experiments, it acts like a stream of tiny particles called photons. This is known as wave-particle duality, and it's one of the cornerstones of quantum mechanics. It was actually Einstein who won his Nobel Prize for proving this, specifically the photoelectric effect, not for relativity. This duality is why light can travel through the vacuum of space, where there's no air to carry a wave, but it can also be focused and refracted by lenses like a physical object. It's a literal bridge between the world of matter and the world of pure energy. 21. Radio waves are the giants of the spectrum. At the very low frequency end of the spectrum, we find radio waves, and they are surprisingly huge. While we can't see them, the wavelengths of radio energy can range from about 30 centimeters long to over 100 kilometers long. Because they're so large and have such low energy, they're incredibly good at traveling through obstacles like walls, trees, and even entire buildings without being scattered. This is exactly why they are perfect for communication. When you're in a basement and still get radio signal, it's because those massive waves are simply too big to be stopped by the atoms in the concrete. They just roll right through, carrying the data for your music or cell phone calls along with them. 20. Microwaves are just high-energy radios. Most people think of microwaves only as the box in the kitchen that explodes your leftovers. But in the spectrum, they're actually just a specific subsection of radio waves. Sitting right between traditional radio and infrared, microwaves have wavelengths ranging from about 30 centimeters down to a few millimeters. Because these waves are shorter, they carry more energy and can be focused into tight beams, which is exactly how your Wi-Fi router sends data to your laptop and how GPS satellites tell your phone exactly where you are. The reason they cook food is actually a very specific trick of physics. The frequency of a standard microwave oven is tuned to vibrate water molecules. When those molecules flip back and forth billions of times a second, they create friction. And that friction creates the heat that warms your soup. It's a perfect example of how humans have tamed a specific slice of the spectrum for pure convenience. 19. The zone of silence and radio quiet zones. Because radio waves are so persistent and travel so far, they can actually become a form of pollution for scientists trying to listen to the stars. This has led to the creation of radio quiet zones, like the one in Green Bank, West Virginia. In this 13,000 square mile area, cell phones, Wi-Fi, and even microwave ovens are technically illegal. Why? Because the giant radio telescopes are so sensitive that they can pick up on the heat of a planet millions of light years away. To these telescopes, a single spark plug in a gasoline engine or a stray Wi-Fi signal sounds like a jet engine screaming in a library. People who live there have to use landlines and wired internet, living in a literal EM time capsule, just so we can keep our ears open to the whispers of the early universe. It highlights just how much invisible noise we usually live in without ever realizing it. 18. Infrared. The light you feel as heat. Moving up the spectrum, we hit the infrared, IR, range, which sits just below the red light we can see. While your eyes can't pick it up, your skin definitely can. We experience infrared radiation as heat. Everything in the universe that has a temperature above absolute zero emits some form of infrared light. This is the secret behind thermal imaging cameras and night vision goggles. These devices don't actually see in the dark, they translate the infrared glow of a person's body heat into colors our eyes can understand. It's also how your TV remote works. Every time you change the channel, a tiny LED on the front of the remote pulses a specific Morse code of infrared light at the TV. You can't see the beam, but if you look at the remote through your smartphone camera, you'll see it blinking, because digital sensors are often more sensitive to the EM spectrum than our own biological eyes. 17. The discovery of infrared was an accident. The way we found out about the invisible parts of the spectrum is a great story of accidental science. In 1800, an astronomer named William Herschel was trying to measure which colors of sunlight carried the most heat. He used a prism to spread sunlight into a rainbow and placed thermometers in each color. Just for a laugh, he placed a control thermometer just past the edge of the red light, where there was seemingly nothing but shadow. To his shock, the thermometer in the dark got hotter than all the others. He had accidentally discovered a form of light that was invisible to the human eye, but packed more thermal punch than visible light. This was the first time humanity realized that the rainbow didn't stop where our vision did, opening the door to the idea that the universe is filled with colors we simply aren't equipped to see. 16. The greenhouse effect is a spectrum trap. Understanding the IR part of the spectrum is actually the key to understanding climate change and how our planet stays warm. Sunlight, mostly visible light, passes through our atmosphere easily and hits the Earth's surface, warming it up. The Earth then tries to radiate that energy back into outer space, but because the Earth is much cooler than the Sun, it emits that energy as long wavelength IR light. Greenhouse gases like carbon dioxide and methane act like a one-way mirror for the spectrum. They let the visible light in, but they absorb and trap the outgoing IR heat, bouncing it back down to the surface. Without this spectral trap, the Earth would be a frozen ball of ice with an average temperature of negative 18 degrees Celsius. The problem we face today is simply that we've made the trap a little too efficient, changing the fate of the entire planet. 15. Ultraviolet, the invisible burn. Sitting just past the violet end of the rainbow is ultraviolet light, UV. Because UV waves have shorter wavelengths than visible light, they carry more energy, enough to knock electrons away from atoms. This is why you don't get a sunburn from standing under a bright indoor lamp, but you do from standing under the sun. The sun's UV rays are powerful enough to penetrate your skin cells and damage the chemical bonds in your DNA. Your body's response to this attack is to produce melanin, a tan, as a shield to absorb future radiation. It's a reminder that the EM spectrum is a physical force that our bodies have spent millions of years evolving to handle. 14. Bees and bullseye flowers. While UV light is mostly a hazard for humans, for much of the animal kingdom, it's an essential part of the visible world. Many insects, especially bees, see the ultraviolet part of the spectrum. If you look at a plain yellow flower through a UV camera, you'll often see a dark, high-contrast bullseye leading toward the center. To us, the flower is one solid color. To a bee, it's a brightly lit landing strip designed to guide them toward the nectar. This shows how evolutionary arms races are fought across the spectrum. Plants have developed invisible colors that specifically target their pollinators' eyes. 13. The ozone layer as a spectral filter. The only reason life on land is possible at all is thanks to a very specific interaction between the EM spectrum and our atmosphere. High in the stratosphere, a thin layer of ozone molecules acts as a security guard for the planet. It's particularly good at absorbing ultraviolet C and most ultraviolet B rays, the most dangerous parts of the UV spectrum. In the late 20th century, humans accidentally began punching a hole in the shield using chemicals called chlorofluorocarbons, or CFCs. Without the ozone layer to filter the spectrum, skin cancer rates would skyrocket, and the base of the food chain, like phytoplankton, would be decimated. It's a sobering look at how fragile our existence is. We're protected from the death rays of the sun by a layer of gas that is in some places no thicker than 2 pennies stacked together. 12. X-rays, the high-speed interrogators. When we jump past UV, we enter the world of X-rays. And here, the penetrating power of the spectrum becomes a superpower. X-ray photons are so small and high energy that they can zip right through the soft tissue of your body, like skin and muscle, without much trouble. However, they struggle to get through denser materials like bone or lead. When a doctor takes an X-ray, they're essentially taking a shadow graph. The light passes through your arm and hits a sensor on the other side, leaving a dark shadow where your bones block the path. Discovered by Wilhelm Röntgen in 1895, X-rays were the first time humanity could see inside a living person without a scalpel, transforming the EM spectrum into the most important diagnostic tool in medical history. 11. X-ray astronomy, seeing the violent universe. Because X-rays are only created by incredibly high temperature events, they are the primary way we study the most violent parts of the universe. While a standard telescope sees the quiet light of stars, X-ray telescopes like NASA's Chandra sees the scream of matter being ripped apart by black holes, or the shockwaves of exploding stars, supernovae. The catch? Earth's atmosphere is so good at blocking X-rays, which is great for our health, that we can't see these signals from the ground. We have to launch telescopes into orbit to see in X-rays. These images don't look like the pretty twinkling stars we're used to. They look like glowing clouds of gas heated to millions of degrees, revealing a hot universe that remains completely hidden to our eyes. 10. Gamma rays, the ultimate energy. On top of the EM ladder are gamma rays. These are the shortest, highest energy waves to exist, and they're often produced by the subatomic decay of radioactive isotopes, or the hearts of dying stars. Unlike X-rays, which are produced by the movement of electrons, gamma rays originate from the nucleus of the atom itself. They're so powerful that they can pass through several inches of solid lead, or several feet of concrete. In the vacuum of space, gamma ray bursts are the brightest events in the universe since the Big Bang. A single burst of it can release more energy in 10 seconds than our sun will emit in its entire 10 billion year lifetime. They represent the extreme end of the spectrum, proving that light can be a force of total localized destruction. 9. Using gamma rays as a scalpel. While they sound terrifying, humans have figured out how to use the extreme power of gamma rays for precision medicine. In a procedure known as the gamma knife, doctors use roughly 200 beams of gamma radiation and aim them with sub-millimeter precision at a tumor inside a patient's brain. A single beam isn't strong enough to damage the healthy tissue it passes through, but at the exact point where all 200 intersect, the energy is high enough to destroy the DNA of the cancer cells. It's essentially surgery without a knife, using the most dangerous part of the EM spectrum as a tool for healing. Also, they can create Hulks, so that's fun. Don't blast yourself with gamma rays hoping to become Hulk. This has been a PSA. 8. The cosmic microwave background, the echo of the Big Bang. If we jump all the way back down to the low energy end of the spectrum, we find a glow that fills every square inch of the sky. This is the cosmic microwave background, or CMB. When the universe began 13.8 billion years ago, it was a hot, dense fireball of high-energy gamma rays. But as the universe expanded, those waves were stretched over billions of years. Today, that energy has been stretched so much that it's shifted from high-energy gamma rays all the way down to low-energy microwaves. This afterglow is essentially a baby picture of the universe, and it's the oldest part of the EM spectrum we can detect. It provides the definitive proof for the Big Bang, showing that the history of our entire existence is written in the shifting frequencies of the spectrum. 7. Why the sky is blue and sunsets are red. Even the simplest things we see are a result of how the EM spectrum interacts with the atmosphere. This is known as Rayleigh scattering. As sunlight, which contains all the colors of the rainbow, hits the gases in our atmosphere, the shorter, higher energy blue waves are scattered in every direction by the nitrogen and oxygen molecules. This is why the sky looks blue during the day. You're seeing scattered blue light. However, at sunset, the light has to travel through much more of the atmosphere to reach your eyes. By the time it gets to you, most of the blue light has been scattered away, leaving only the longer, sturdier red and orange waves to pass through. It turns the entire sky into a giant prism, sorting the spectrum by wavelength right before your eyes. 6. The water hole and searching for aliens. The EM spectrum isn't just for science. It might be our best shot at making first contact. Between the frequencies of 1.4 and 1.7 gigahertz in the radio part of the spectrum, there's a very quiet region known as the water hole. This area is bounded by the radio signatures of hydrogen, H, and hydroxyl, OH, which together make water, H2O. Because this part of the spectrum is naturally quiet and universally recognizable to any species with a basic understanding of chemistry, astronomers at SETI, the Search for Extraterrestrial Intelligence, believe this is the frequency where an alien civilization would most likely broadcast a signal. It's like a universal meetup spot on the dial, a specific slice of the spectrum where we hope to one day find a hello from across the stars. 5. Magenta color doesn't actually exist. One of the biggest lies your brain tells you is the color magenta. If you look at the EM spectrum, every color has its own specific wavelength. Red is long, violet is short. But if you look at a rainbow, there's no magenta between red and violet. So why do we see it? When your eyes detect both red and violet light at the same time, your brain has a problem. It can't find a single wavelength that represents both. Instead of showing you two separate colors, your brain invents a brand new one to bridge the gap. Magenta is a purely psychological construct. It's a spectral bridge that your mind builds to make sense of the two opposite ends of the visible spectrum hitting your retina at once. 4. Light can actually push things. We usually think of light as being weightless and ghost-like, but photons actually carry momentum. This is the principle behind solar sails. Just as a sailboat is pushed by the wind, a spacecraft with a massive reflective sail can be pushed through the vacuum of space by the literal pressure of photons hitting it. While the push from a single photon is incredibly tiny, over time, a solar sail can accelerate a craft to incredible speeds without using a single drop of fuel. NASA and other space agencies are already testing this technology, proving that the EM spectrum isn't just a way to see the universe, it might be the engine that eventually carries us to other star systems. I mean, they use light bridges in Portal and solar sails in both Star Wars and Tron, so yeah, let's do it. 3. The redshift of the universe. The EM spectrum is the ultimate speedometer for the entire universe. Because of the Doppler effect, when a light-emitting object, like a galaxy, moves away from us, its light waves get stretched out. This stretching moves the light toward the red end of the spectrum, a phenomenon called redshift. By measuring exactly how much the light from distant galaxies has shifted toward the red, Edwin Hubble discovered that the universe is not static, it's expanding. The further away a galaxy is, the faster it's moving, and the more reddened its spectrum becomes. Without this specific quirk of electromagnetic waves, we would still think we lived in a small, unchanging universe, rather than an explosive, growing one. 2. We are literally made of EM interaction. At the most fundamental level, you only exist as a solid object because of the EM spectrum. The reason you don't fall through your chair or walk through walls is due to the electromagnetic force between the electrons in your body and the electrons in the objects around you. Like two magnets of the same pole repelling each other, your atoms are pushing against everything else. This force is carried by virtual photons, the same fundamental particles that make up the spectrum. On a subatomic level, every touch, every breath, and every heartbeat is a high-speed exchange of electromagnetic energy. 1. The heat death and the last photon. The ultimate fate of the universe is tied directly to the spectrum. Right now, the universe is filled with high-energy light from billions of stars. But billions of years from now, after the last star has burned out and the last black hole has evaporated, the universe will reach a state called heat death. At this point, the expansion of space will have stretched every single wave on the EM spectrum to such an extreme degree that their wavelengths will be longer than the observable universe itself. So, the energy will be so spread out that no work can be done and no life can exist. The final event in the history of the cosmos will be the last few photons of the EM spectrum stretching into total, absolute nothingness. From the radio waves that carry our voices to the gamma rays that forge the stars, the EM spectrum is the invisible thread that binds the entire universe together. It's a reminder that what we see with our eyes is just a tiny, tiny fraction of the real world. If you enjoyed this dive into the EM spectrum, well, you'll love our video on 25 crazy science facts you may not know. That'll be popping up here any second now. Thank you guys so much, and as always, like, share, comment, subscribe with that notification bell, and I'll catch you in the next one.